Hi everyone, today I will present our work Drift with Devil, Security of Multi-Sensor Fusion-Based Localization in High-Level Autonomous Driving under GPS Spoofing. My name is Junjie Shen. Me and my co-authors are all from AS Guard Research Group, or Autonomous System Guard Group at the UC-Irvine, under my advisor Shen. As many of you are already aware, the autonomous vehicles are finally on public roads. For example, the picture on the right are taken at Irvine, where you can get free rides of self-driving taxis by simply typing on your smartphone. However, many of us still have concerns about the safety of this brand new technology, especially when the safety issues can be deliberately triggered by the attacker. Before I jump into our attack, let's first take a look at the internals of an AV. Typically, a Level 4 AV comes with a lot of sensors, such as LiDAR, GPS, IMU. These sensor inputs will be passed to an autonomous driving system or AD system to make driving decisions. For example, Localization module uses sensor inputs to estimate the current position of the vehicle. Perception module then uses the sensor inputs and the localization output to detect the surrounding obstacles. Next, Planning module will calculate an optimal driving trajectory based on the obstacles and the vehicle position. Finally, the Control module enforces this plan by correcting any deviation between the localization output and the planned trajectory. Localization is critical to the safety of AV. If localization is inaccurate, the output of localization will have some deviation to the actual position of the vehicle. Because of the Control module, these deviations will be directly reflected in the physical position of the AV. And if the deviation is large enough, it can cause the AV to drive off-road to hit the road curb, or even onto a runway to crash into another vehicle. For AD localization, GPS is the de facto location input. However, it is well known that GPS is susceptible to GPS spoofing attacks, where the attacker sets arbitrary position by sending fake satellite signals. GPS spoofing is still an open problem because of the lack of authentication, and it has been demonstrated to be practical on a lot of end systems. In fact, GPS spoofing activities are becoming more pervasive recently. Last year, it is reported that over 9,000 spoofing activities are identified in Russia since February 2016. Fortunately, for AD systems, GPS is not the only positioning source. Instead, they widely adopt a multi-sensor fusion or MSF-based design, as in commercial AD systems, and studied in many research works. Different sensors have different properties, so the core idea behind the MSF is to leverage the strength and compensate the weakness of these sensors to generate improved accuracy and the robustness. So far, the most popular MSF fuses sensor data from GPS, LiDAR, and IMU. And the state-of-the-art one can achieve localization accuracy as small as 5.4 cm. As we can see, in MSF, GPS alone can no longer dictate the localization results, and that is why MSF is generally believed to have the potential to defend against the GPS spoofing. However, none of these prior works studied whether state-of-the-art MSF algorithms are indeed sufficiently secure under GPS spoofing. In our work, we are the first to explore this highly critical but completely unexplored problem space. According to our study, the short answer to this is no, as long as the spoofing is done strategically. First, let me show you an end-to-end demo of the attack discovered in our work, called Fusion Reaper. We created this attack demo using an AD simulator and the end-to-end Baidu Apollo AD system. Here, the left side is the MSF view, and the right side is the physical world view. The red circles are the LiDAR positions, and the blue circles are the GPS positions. And the green circles are the MSF output, which is where the victim thinks it locates. And on the right is the physical world position. This is where the victim actually is. First, let's see how the victim AV drives without any attack. We can see that the victim safely went through the traffic lane. Next is with our Fusion Reaper attack. Here, the attacker started the first stage of the attack. I will talk about the attack details in the later slides. Now the attacker starts the second stage of the attack. As we can see, the attacker drags away the MSF output to the left and causes the victim to deviate to the right in the physical world, and finally hit the stop sign. Now let's take a look at the details of our research. We formulated the problem as the attacker spoofed GPS inputs with certain distances to victim's physical position. Attacker tries to maximize the lateral deviation in the MSF output compared to no attack. In this figure, the attacker spoofs the GPS to deviate the MSF to the right. But because of the control module, the physical position of the vehicle is actually deviating to the left. Then in terms of the attack goal, the attacker tries to introduce a deviation that is large enough to cause the victim to drive off-road or onto a runway. In this work, we call them off-road and runway attacks. As the first step, we did a security analysis to understand the security properties of MSF. In this analysis, we aim to find the maximum possible deviation that can be achieved by GPS spoofing. Our analysis target is the production-grade Baidu-Apollo MSF, which is representative in both design and implementation. From our security analysis, we find that MSF can indeed improve the security against the GPS spoofing. However, we also find a very interesting takeover effect, which can cause an exponential growth trend of the deviations, as one shown in this figure. In such case, the spoofed GPS inputs become the dominating source to the phishing process, and can even make the MSF algorithm to drop the data from all other sources. This is why we call it a takeover effect, which fundamentally defeats the design principle of multi-sensor fusion. We then did a statistical causality analysis and find that such a takeover effect is created by some dynamic and non-deterministic factors, such as sensor noises and algorithm inaccuracies. This makes it difficult for the attacker to predict or control such vulnerability. To overcome this, the attacker has to exploit it in an opportunistic way. To do that, we designed Fusion Reaper, which is a two-stage attack with a vulnerability profiling stage and an aggressive spoofing stage. Here is an illustration of this attack. In the first stage, the attacker tries to find out where the vulnerable period appears. After finding out such a vulnerable period, the attacker launched the second stage to aggressively spoof the GPS in order to take over the MSF and cause large deviations. We evaluated the attack on 6 real-world sensor traces. We found that there always exists at least one attack parameter that can achieve over 95% success rates to cause lane departure or runway driving. It is also pretty fast, with only about 30 seconds to succeed on average. We also find that our attack is robust to practical attack considerations such as spoofing inaccuracies and AD control. We also did more extensive evaluations such as abolition study, generality analysis, comparisons with naive attacks, and also black box attack designs. Please refer to our paper for more details. There are two general directions to defend against Fusion Reaper. First is to fundamentally prevent the attack by either prevent GPS spoofing or improving the sensor and the localization technologies. However, currently these fundamental solutions are not immediately deployable. Second, and a more actionable mitigation, is to apply attack detection and emergency stop. For example, using GPS spoofing detection or camera-based lane detection. Such a solution is still limited though. For example, it can still cause denial of service of the AV operation. But we think it's still better than directly causing the safety damages that we have shown earlier. We did a responsible vulnerability disclosure to the AV companies after this paper is accepted. As of July 20th, we have informed the 29 companies which are developing or testing level 4 AVs. Among them, 16 have replied and started the investigation, and one company is currently working on a fix. To conclude, we performed the first security analysis on MSF-based AD localization under GPS spoofing. We discovered a takeover vulnerability which fundamentally defeats the design principle of MSF. We designed a concrete attack called phishing reaper to opportunistically capture and exploit this vulnerability. We also designed an offline profiling method to improve the attack practicality. Finally, we have informed the 29 AV companies regarding this issue. With that, I want to thank you for your attention, and I'm open to any questions.